Okay, and we are back. And today we're going to be going over one of my favorite machine learning algorithms, logistic regression. And so immediately when you hear the word regression, you probably think back to one of the two types of supervised learning where we make predictions with the regression. This is what we did with the linear regression and with the multivariate linear regression. We made predictions for some inputs. We received, in our examples, square footage of a house, the number of bedrooms, the number of floors, all of that, and then we would output some price for the house. And one thing to keep in mind is that when we send our inputs into our normal linear regression, um, linear, we would wind up with an output. It was a price, and that price was a continuous variable. It could have been 317,234. Anything we can think of, any number, it could have output for the price. So that was with the linear regression. Now we're going to be taking our inputs for logistic regression and doing something completely different. So in this case, we're going to be outputting a class. In our case, if we use binary classification, binary output. And what do I mean by a binary output? It is either a 0 or a 1, where these are the two classes that we're going to be sorting our data into. A 0 indicates the absence of something, and 1 indicates the presence of something. And so what logistic regression is going to do, we feed it some inputs, and then it will output either a 1 or a 0, depending on whether it actually has the presence of a characteristic or that characteristic is absent. So an example would be I send in an email, and then it tells me if it's spam or not. Now in this case, the not would be the absence of spam, and the 1 would indicate the presence of spam. So 0 for the not and 1 for it includes that. And maybe we have a tumor, and it could be cancer or not cancer. And so even though it seems like we're only sorting things into one of two classes, that couldn't be all of that powerful. It's actually an extremely powerful technique that's used to tell whether the presence of something is in your data input or not. And so that is a very, very valuable trait to have for some sort of algorithm. So before I move on any further, I need to talk about one thing. Let me go ahead and clear the board and talk about what we have here. So logistic regression. If we're going to be looking at our inputs coming in and outputting just a group, a 0 or 1 belonging to one group or the other for our inputs, why do we use the word regression? And the answer is it's kind of a misnomer. It is not what it should be labeled, but we are stuck with the term. One of the reasons is that in logistic regression, we are going to be actually our input that we're sending into our logistic regression is going to be, let me do that, a linear regression type input. So we're going to feed in our linear regression input into logistic regression, and then it will output either a 0 or a 1, depending on which group it thinks the input belongs to. So that's the only reason I've ever heard why it's called logistic regression, is because we're feeding in a regression and we're feeding it into a logistic formula that we'll get more into that as we go through the cost function. But the regression really shouldn't be called regression, but in this case we're stuck with it because that's what everyone calls it. And the reason is that I believe we're sending in a linear regression as our input and into our hypothesis function, and we will be outputting a group. So that's the overall basics of what logistic regression is doing, and we will pause here and pick right back up. Okay, so the first thing that I want to talk about is comparing linear regression output to logistic regression. And so linear regression, like we talked about earlier, when it outputs, it's some sort of continuous variable, I can spell, variable that can take on any value that our hypothesis function gives us. So it can be 213,000, 392,000. All the different outputs are available for the linear regression. The logistic regression, though, all we want is for it to output a 0 or a 1. So instead of our hypothesis function mapping into a continuous, we want it to map into a 0 or 1. So the way that we do that is we start off by taking our hypothesis function. We're going to start off with our good old theta transpose x that you saw with the multivariate linear regression. So that one was just, we had theta 0, x of 0, plus theta 1, x of 1, plus dot, 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 all the way out to theta sub m, x of m, something like that. And so this was our hypothesis function for linear regression. So that was our hypothesis function. So now what we're going to do is we're going to take that same hypothesis function and we're going to feed it into a function that will map the outcome to either a 1 or a 0. So we're going to take our theta transpose x and use it in the following form. Our h of x for logistic regression is going to be 1 over 1 plus e to the negative theta transpose x. And this is a very special function. We're going to feed in the standard hypothesis function that we use for a multivariate linear regression, the theta transpose x. We're going to feed it in right here at the top of the exponential. Now, this function is called the sigmoid function. And its job is to take any input and output a value between 0 and 1. So if we look at, let's let our theta transpose x be much less than 0. Okay, if that's the case, then I'm going to get 1 over 1 plus e to the, if it's much, much less than 0, I can think about plugging in at this point a negative, something approaching negative infinity. So a very, very small negative number, or a large negative number if you're talking about the magnitude. And when this happens, I'm going to get, for my value, 1 over something that is growing without bound. So it's similar to 1 over infinity, which becomes a 0. If we have a constant on top and we divide by infinity, that is always going to be heading towards 0. And I'm not using the limit definitions from calculus because it would complicate things a little bit, and I think this kind of gets the point across. But now if I let my theta transpose x value be much greater than 0, well, in that case, I'm going to have 1 over 1 plus e to the negative positive infinity. So the theta transpose x, we're saying, is approaching infinity, a very, very large value. So in this case, I'm going to have 1 over 1 plus this value right here is going to 0, which is going to wind up outputting a 1. So very negative numbers will output a 0 with the sigmoid, and very positive numbers will output a 1. And then just for completion's sake, let's let theta transpose x equal 0. So if it's equal to 0, I'm going to get 1 over 1 plus e to the negative 0, which is just going to be 0, which means I'm going to get 1 over 1 plus 1, which is 0.5. So I have with the sigmoid function, a function that is going to map negative values to a 0, positive values to a 1, and then values that are exactly in the middle are going to map out to 0.5. So this 0.5 is going to be kind of a boundary. We're going to say that anything, when I run the sigmoid function, that is greater than 0.5 as an output, that indicates the presence of something. Anything that is less than 0.5 is going to indicate the absence of something. So just as a recap, this is the presence of some characteristic, and this is the absence. Alrighty, so there we have it. Our new hypothesis function is going to be the sigmoid function, where the argument that we're feeding into the exponential is actually the good old multivariate linear regression theta transpose x. Okay, so I would be remiss if I didn't actually draw out the sigmoid. It really helps to visualize moid function, what the function is doing when you get a graphical representation. So I'm going to put a 1 mark here at 0.5, and now I'm going to draw the sigmoid. And so the sigmoid crosses right here and then tails off. So if this is a 1, we can say that we basically have a horizontal asymptote that the sigmoid approaches as it heads towards positive infinity. So all the positive values, x equals a positive value, you have the sigmoid mapping into and approaching 1. When I have a negative value, on the other hand, I have a horizontal asymptote that the sigmoid is approaching here. I'll put the little arrows on there. So all negative values, it maps towards a 0 for the sigmoid function. And when x is actually equal to 0, we have the sigmoid crossing right at y equals 0.5. Okay, so now let's write our hypothesis function up at the top, and we have our hypothesis is 1 over 1 plus e to the negative theta transpose x. That is our original linear regression, and we're feeding it into the sigmoid function so that it will output a 0 or a 1 or something in between. So one of the ways we can think about this in a very rough way is that when I feed in my linear regression and I get an h of x, oh, maybe it's 0.7. Roughly, very roughly, you can think of corresponding to kind of a percentage that the value, the input rather, is going to be sorted into the first category, the 1 category. So 70% chance that y is equal to 1. And same thing for if we have low probability, or I keep saying probability, but it does not map 1-to-1 into the probability. We have maybe 10% chance that y is equal to 1. And you can kind of think about this as corresponding to if I now have h of x equal to 0.5 or greater, it's more likely that I have y equal to 1. And if it's less than 0.5, it's more likely that y equals 0. Okay? So now that we have that defined, let's talk about our cost function. So our cost function, if I can delete this, there we go. Our cost function for the linear regression was, let's see, 1 over 2m summation I from 1 to m of, we had our h of x I minus y I, right? And so this gave us our MSE, the mean squared error, okay? Now, what we did with this is we wound up taking the derivative of the cost function in order to use our gradient descent. So it looks like the cost function is a good place to start when we're talking about the logistic regression. But looking at the way that the cost function is defined up here, like we can already see that it's not going to handle the sigmoid function very well, because what this does is it compares an actual y value to the hypothesized value here for the hypothesis function. But what we want is we want it to make a guess of whether or not the input is either belongs to y equals 0 or y equals 1. And so we're not going to use this cost function when we're talking about logistic regression. Instead, we're going to define a completely new cost function that works better with classifying whether or not an input belongs to the first group or the second group. So we have the cost now is going to be, here we go, piecewise function, everyone's favorite. It's going to be negative log of h of x, and this is if y equals 1, and negative log of 1 minus h of x if y equals 0. Okay, that looks like it fell straight out of the sky. There's no real reason for it to be that way. So what we're going to do is we're going to break it down one case at a time. Okay, let me clear this. Now, first one, we're going to do the case where y equals 1. Okay, we said that that would be the negative log of h of x. Okay, now what does that look like as far as graph? Well, it looks like this. With my beautiful artistic skills, I will have the cost function on the y-axis, and I will have my h of x on the x-axis, and it looks like this. Okay, so we'll call this 1. What this, and of course this is 0 over here, right here. So what this says is, with this function, if y is actually equal to 1, and I guess a 1, then I'm going to have a very low cost. As a matter of fact, it will be near 0. So if y is equal to 1, and I guess y equals 1, then the cost is very low, approximately 0, because it would be located right here. Okay? Meanwhile, if I have an h of x that leads me into guessing that it is group 0, so let's say I have something like here, if I now look at the cost associated with that, it's very high. This is heading towards positive infinity right here as I get close to 0. So if y is equal to 1, and I guess I just said 1. Let me make that a 1 right there. And I guess y equals 0, then cost is much greater than 0. It's a very high cost. So what this does, which is really fascinating, setting this up this way, is that if my h of x winds up being a very positive value near 1, the cost is going to be nearly 0. If the h of x is very low and I wind up guessing a 0, the cost is going to be very high. So what this does is it rewards guesses that are close to the actual y value, the input, rather the output. It rewards if it matches, in this case y equals 1, and it severely punishes if it gives an incorrect guess. So that is what we're going to be using for our cost function in the case where y equals 1. Okay, so let's clear the board and do the next piece. And so we have the case where y equals 0. The case, if I can draw that, where y equals 0. Okay, we said that was going to be negative log of 1 minus h of x. Okay, so what does that look like? Well, without drawing it out based on what we saw before, if y is equal to 0, and I guess 0, and this is again the cost, and this is h of x right down here. So if y actually does equal 0, and I guess 0, I need to have a very small cost. So I'll just put something here, and if my guess is that it's that the category is 1, where h of x is closer to 1, I need to have a really high cost associated with that. So I need to punish that. What does this graph look like? Well, it looks like this. So again, this is exactly what we want. If y is equal to 0, and I guess that y equals 0, the cost is approximately 0. And if y is equal to 0, and I guess y is 1, then the cost is much greater than 0. So we're using these two log functions to represent the costs associated with making a guess for which group an input belongs to. And it heavily penalizes any guess that is not correct. And the worse the guess is, the more it penalizes it. And the better the guess is, the lower the cost, and it goes very close to 0 at this point. So that's the way that our new cost function is going to work. Now for some math. Okay, let's clear this and go through some math, which is what I tend to enjoy. So we're going to start off with our two cost functions when in the piecewise form. We had the cost is equal to, we have negative log of h of x if, and this is y equals 1, and negative log of 1 minus h of x, and that's if y equals 0. So what we're going to do is we're going to combine both of these pieces into a single cost function. And this is one of the nicest math tricks you're going to see all day. So to combine these in, I want this function, the top one, I want that to survive when y is 1. So when y is equal to 1, I use this function. And when y is equal to 0, I want to use this function. And the way that you do that is you set up something that looks like this. The cost is equal to, I've got negative y times log of h of x, and then that's going to be minus 1 minus y times the log of 1 minus h of x. There we go. So this is called the log likelihood function. So log likelihood, I hope I spelled likelihood correct, function. Okay? And it's really extremely clever because if y is equal to 1, then the second piece, this will become a 0, and this piece will go away, which reverts to only the first part here. Meanwhile, if y is equal to 0, this piece, this would be a 0 here, would go away, and I would be left with 1 times this piece, which is this. So this combined function here is incredibly elegant. It's one of the nicest tricks I've ever seen in math, to where I can have this combination function, and depending on whether y is 1, it'll be this piece, or if y is 0, it'll use this piece, and it will eliminate the other. That's a nice trick. So now that we have this beautiful cost function, this log likelihood function, we need to do one more thing before we can get to gradient descent. And that is, we need to have the derivative of the cost function, because that's what's going to be needed for gradient descent. And yes, we are going to use this function right here when we do the derivative. So get ready for a lot of math using logs over the next section. Luckily, I have it all typed up, so it won't be as bad as writing it would be. So here we go. Okay, so here we go with the actual cost function, and it's going to be our j of theta is equal to negative 1 over m summation from 1 to m of the log likelihood function that we just went over, y times the log of h of x plus 1 minus y times the log of 1 minus h of x. And I'm using the superscript I because that's going to be important as we move along. The other thing to note is that this log that I keep referring to right here, it is the natural log. I didn't write it as ln, I wrote it as just log, but just keep in mind that its base is base e. Alrighty, so we're going to start off with this function right here, and then if I can get it to actually, there we go. I'm now going to take this function and simplify two of the terms in here. First one is going to be this log of hx of I, and then the second one will be the log of 1 minus h of xi. So here we go. Start off with this one. So first thing I do is I convert my hypothesis function, my h of x, into the actual sigmoid, 1 over 1 plus e to the negative theta xi. And notice that there is not a little superscript t by the theta. This isn't theta transpose x according to what's on the screen, because it's missing the t, but it is indeed theta transpose x. It's just really hard to see the t once we get to smaller exponents like this. So I'm just going to leave it as theta x. There's going to be an awful lot of these, and I'd hate to say theta transpose x every time. So when you hear theta x, think theta transpose x. So here we go. So I have the sigmoid function written out here, and I'm then going to convert this into the denominator to the negative first power. So I just popped it across the divider bar and changed the positive 1 exponent that's lurking out here that is not visible into a negative 1. And then I use the property of logs to bring the negative 1 exponent out to the front of the logarithm and wind up with negative log of 1 plus e to the negative theta x. Alrighty, so that's that piece. And then let's look at simplifying the second piece. So second piece, we start off the exact same way. We have 1 minus h of x of I, or xi I should say, and then I just convert that h of x into the sigmoid. So 1 minus 1 over 1 plus e to the negative theta x. And so the next step is we're going to use a math trick. I'm going to find a common denominator for my 1 here. And so I'm going to put the denominator of the sigmoid on top of itself. So this is going to be 1 plus e to the negative theta x over 1 plus e to the negative theta x. Now, since these have the same denominators, I can now take the 1 over here and subtract the 1 over here to wind up with a 0 for my constant term, and that will leave e to the negative theta xi over 1 plus e to the negative theta xi. Now, since this is a logarithm of a division, I can change that using the property of logs to a subtraction of logs. So it would be the log of the numerator, log of e negative theta x, minus log of the denominator, 1 plus e to the negative theta x. Okay, last thing I'm going to do is, since this is the natural log, when I take the natural log of the exponential, those are inverse functions of each other, and so they wind up canceling. And so all I'm left with is just negative theta x minus log of 1 plus e to the negative theta x. Okay? So now I'm going to substitute that back into my expression, and I'm going to get the new cost function, negative 1 over m summation y times this new piece, negative log of 1 plus e to the negative theta x plus 1 minus y times this new expression, negative theta x minus log of 1 plus e to the negative theta x. So that is my new cost function. Okay, and it looks like we're spending a lot of effort to make things look worse, but I promise there's a huge payout at the end if you can just bear with me till we get to the very end. This is actually one of the nicest mathematical derivations I've ever seen, so I hope you enjoy it. So the next stage is we're going to start with this as our cost function, the very bottom expression. So here we go. It's up top, and so now we are going to work some magic. We're going to distribute this 1 minus yi through this expression here. And so when we do that, we wind up with our cost function is equal to negative 1 over m summation I from 1 to m of yi times negative log of 1 plus e to the negative theta x plus 1 times that just gives us that. So negative theta x minus log of 1 plus e to the negative theta x plus, now it's going to be, because it's minus times the minus, so the minus signs are canceling over here. So we have plus yi times theta x plus log of 1 plus e to the negative theta x. Okay, so that's the first step. And for the next step, I'm going to distribute this yi through this expression right here. So the top part, only thing that changes, the left part, the only thing that changes is I pop this negative sign out from in front of the log to in front of the yi. So this becomes negative y log 1 plus e to the negative theta x plus theta xi minus log of 1 plus e to the negative theta x plus, now I'm distributing the yi, so this becomes yi times theta xi plus yi times log of 1 plus e to the negative theta xi. Okay, notice that we now have positive yi log of 1 plus e to the negative theta x and negative yi log of 1 plus e to the negative theta x. So I can now combine them, and they'll cancel out, and it leaves the following expression. We have our negative 1 over m, summation from 1 to m of what's left, this piece right here, negative theta x minus log of 1 plus e to the negative theta x, plus this term right here that survived, y theta x. So now we're going to simplify this term. We're going to rewrite it into a different form, the term in green here. And so we start off, we have that expression, and the first thing that we're going to do is a very strange looking trick. We are going to take this theta xi and change that into the log of the exponential of theta xi. Okay, so that's basically the opposite of a trick that we used earlier where they were inverse of each other and they became a 1. Now we're using the property that they are indeed a 1 to basically rewrite them into that form. And then that's just minus the log of 1 plus e to the negative theta x. Okay, I'm going to factor out a negative 1 from all of that. And then after I do that, I'm going to use a property of logs that the addition of logs can be written as a single log with a multiplication. So this log of e to the theta xi plus log of 1 plus e to the negative theta xi can become log of e to the theta xi times 1 plus e to the negative theta xi. So all we do is convert that addition to a multiplication. But now when we send the e to the theta xi through, one of the things it's multiplying against is the second term here, e to the negative theta xi. So positive xi, theta xi times negative theta xi, those two exponents become a 0, which is going to leave us a 1 for our result down here. So this becomes negative log of the 1 that I get from multiplying the two exponentials together, plus the e to the theta x times 1, which just leaves e to the theta x. Okay? So with all of that, I now have a new expression. I have my cost function, j, is equal to negative 1 over m summation I from 1 to m of, well, it's the original piece I started with, but reordered now to come at the beginning. So now it's yi theta xi, and then the simplification that we did for the expression in green, minus log of 1 plus e to the theta xi. Okay, we are more than halfway there. It looks like we have definitely shortened the cost function here into a much more manageable form than what we started with the log likelihood. Log likelihood, I should say. Alrighty, so here we go. So starting with that, we're now going to take the derivative of the cost function with respect to theta j. Okay, so when I do that, I get negative 1 over m summation I from 1 to n, the partial of that. Now keep in mind this is taking the partial with respect to theta j. So every other theta j, or theta rather, is treated as a constant. When I take the partial derivative of something like this, where it's theta xi, the only theta that will not be a constant is theta j. So what I'm going to be left with is, when I take the partial derivative of theta times x, the only theta that survives that process is the theta j that is paired with the x sub j. So keep that in mind as we progress. That's why we're going to have subscripts on our x's now. So when I take this partial derivative, I'm going to be left with yi xi sub j, because that's the only part that survives when I take the partial with respect to theta j, minus, so at this point, when I take the derivative of the log function, that is the derivative of the function inside of the log over that thing that's inside the log. So it's the derivative over the actual original expression untouched. So that gives me my theta, my e to the theta xi over 1 plus e to the theta xi. But I'm not done yet, because the chain rule kicks in, and I now need to take the derivative of this theta xi. Well, the derivative of the theta xi with respect to theta j leaves xi sub j. So that's where this x sub j comes from. It is the derivative of this theta xi that kicks in because of the chain rule. Alrighty, so now that we have that, we're going to do something kind of strange. We're going to leave the first term completely untouched, minus xi sub j, that's untouched, times, now to get to this piece, we divide every single term in the previous step by e to the theta xi. If I divide the top by e to the theta xi, I get a 1. If I divide 1 by e to the theta xi, I get e to the negative theta xi. And then if I divide e to the theta xi by itself, again, I get another 1. So this expression, this term right here, becomes 1 over e to the negative theta xi plus 1. All right, here we go. We're getting there. Now, if you look at what we have written here, I'm going to swap the order of the terms, and then I'm going to look very carefully at this term right here, because the 1 over e to the negative theta xi plus 1 could be written where the denominator pieces are flipped. So this would be 1 over 1 plus e to the negative theta xi. And that is our hypothesis function. That's the sigmoid. So now down here, I have this negative sign out in front of my 1 over m. I'm going to distribute it through. So this becomes positive 1 over m, summation I from 1 to m of, I've got my x of ji right here, times my hypothesis function, the sigmoid, minus yi x of ji. Okay? Almost there. I'm going to do one last thing now, and then I'm going to factor out of this expression my xi sub j. Okay, when I do that, I get 1 over m, summation, 1 to m, hypothesis function minus y times x of j. Okay, go to the next piece. There we have it. The partial derivative of the cost function with respect to our theta j is 1 over m, summation, 1 to m, hypothesis function minus our y times x of j. I hope this looks familiar, because what we've just done is we started with the cost function, which is in the form of the log likelihood. With all of those logs, we did a bunch of substitutions and a bunch of tricks with the properties of logs, and out pops this expression right here. This is the exact same expression that we had when we did our linear regression, our multivariate linear regression. This is exactly what we came up with. It is 100% identical, even though it started off looking nothing like this. Now, here's the kicker. Is it the same? It's in the same form, but there's one big difference. That's that right there, that difference is the hypothesis function. The hypothesis function for the multivariate linear regression was theta transpose x. The hypothesis function for logistic regression is the sigmoid, 1 over 1 plus e to the negative theta transpose x. That's it. That's our difference. So now that I know that the cost function, the derivative of the cost function is pretty much identical to that of multivariate linear regression, I can take great comfort in that. That's part of, I'm guessing, one of the reasons that we call it the logistic regression, is because it also has a lot in common with our multivariate linear regression. I really hope you enjoyed that derivation. That is one of my favorites. If you had asked me, would it be possible to get back to this expression from the log likelihood function? No. I would have definitely said no before working through all the gory details. So now that we have this, we're ready to actually dive into the algorithm. So to start, we're going to begin with the linear regression expression that we had for the h of x, and that was theta transpose x, which was theta 0 x0 plus theta 1 x1 plus ... all the way out to theta sub n x sub n. Okay? Then as we moved into logistic regression, the hypothesis function needed to map into a value between 0 and 1, so we use the sigmoid. So that is 1 over 1 plus e to the negative theta transpose x. Okay? Now with that new hypothesis function, we go from there into a new cost function. So we started out with cost function j of theta. And that's equal to we had negative y times the log of h of x minus 1 minus y times the log of 1 minus h of x. Okay? With this cost function, we called this section right here the log likelihood. And we did a fairly substantial derivation to get the derivative of the cost function, the partial of j with respect to theta sub j, and that wound up being just 1 over m summation I from 1 to m of, we've got our hypothesis function minus the actual y value times x sub j. Okay? That wound up being identical in its functionality to what we saw in linear regression, except the difference is the hypothesis function is now different. Okay? Now, the last step is we use gradient descent. Gradient descent. And gradient descent is where we're going to change all of our theta, our parameters, our theta values. So theta sub j gets theta sub j minus alpha, our step size, times the derivative of the cost function. And what this derivative of the cost function does is it tells the algorithm in which direction and with what magnitude do I change my new theta value. So it will say whether I need to add a value to my theta sub j or subtract a value, and how much of that. So the magnitude of the change. So this is right here exactly the same as we've seen before, and this ensures that the new theta values are equal to the old theta values plus some change in the correct direction. We're not guessing randomly with machine learning. We are updating our theta values, our parameters, our weights, if you will, by using the derivative of the cost function every time. This is what allows us to actually train our algorithm to do something useful. It's because we are relying on gradient descent and this partial derivative of the cost function to actually arrive at a better guess each time we loop through. And that is pretty much exactly the way all this is built. We start with our new hypothesis function. We develop a new cost function. We take the derivative of the cost function that's then used inside gradient descent to tell us how to update our theta values, our parameters. And that's it. That is exactly how logistic regression works. The next video will have an actual example of running the code for logistic regression on a nice data set. We're going to use logistic regression to tell us who would live and who would die on the Titanic based on the passenger manifest only. So I look forward to seeing you next video.